Okay, last time we discussed the factors affecting the strength of your concrete. So we have finished up to I think we have finished up to the size and shape of okay size and shape of your specimen. Or rather the test age. Okay, so we're going to discuss a few more on the size and shape, but we have practically finished the material characteristic and proportion, the test age. So this has some more. So we now continue on curing condition first, and then we discuss a little more on the size and shape and the rate of loading. Okay. Okay. So for the curing condition, so curing is simply defined as the simply, no? So in simple language, uh, simple definition, we define curing as simply the control of both humidity and temperature. Okay. So on the humidity control, our ideal humidity, of course, is 80 to 100%. And for temperature, this actually varies, no? Varies depending on the temperature of cast and curing. Okay, so there are two types of temperature control that we are into. So the first one is on the casting, and the next is on the okay curing. Okay, so humidity in hydration, as I have told you, must always be satisfactory, um, ranging from as high as 100% to a minimum of at least 80%, or else hydration stops. Okay, so hihinto yung hydration pag bumaba. So magastos sa tubig yung curing, kaya kuminsan di natin pinapansin yan. Now, regarding the temperature, or the range in which temperature must be within the casting and curing period is from 4.4 to 46.1 degrees Celsius. So this is not a problem when you are in a tropical climate like us, no? So tropical naman sa atin to. Ang nagkakaproblema lang dyan, yung pag masyadong malamig, at kuminsan yung talagang masyado naman mainit, no? So kuminsan umaabot din ng 50 degrees yung up to 60 degrees yung sobrang init, no? Celsius. Okay, so in this temperature, it is observed that at up to 28 days, the higher the temperature, excuse, the more rapid the strength gain in the later ages are reduce. Okay? So, anong ibig sabihin nun pag nandun tayo sa medyo upper boundary, yung reduction natin sa strength gain, okay, so if our graph for the strength gain is like this, okay, we're talking of the later ages here, so the reduction to the increase in strength gain is more rapid here. Okay, so medyo mas pababa siya dito, okay? So later ages, our graph will look like this. So this is strength versus, okay, time. So ganyan yung graph natin. So varying casting temperature with constant curing, these are problems on tropical climates na pag biglang umulan, okay, so the uh, the temperature drops from a very high and then to a little bit lower temperature, but of course the difference is not that big. So this is now your observation on the condition, no? Set as the temperature of casting varies with the curing temperature. Okay, so meaning to say your temperature of casting is not the same, and then when you cure it, of course, constant curing temperature, you have to see to it that during rainy seasons, your concrete, uh, newly poured concrete must be controlled as far as the temperature is concerned. Okay, so with low temperature curing, relatively more uniform of microstructure accounts for a higher strength. So mas gusto natin yung curing procedure natin is done on a cooler, okay, environment. Okay? So curing. So kung kung umuulan, nagbuhos ka and then malamig yung temperature mo do sa lugar, a little bit humid region like Baguio, mas okay yon. Okay? So pag mainit naman ang araw, ganun din, no? So even though kesa yung biglang malamig, tapos biglang pag nag-cure ka na, sobra kainit. Okay? So mas mahihirapan kang ma-attain yung uniformity on the microstructure. That's why the reason why yung pozzolan maganda sa mga ganyang klaseng environment kasi slow yung reaction niya. Okay? So just remember that. So let's go back on the part here na hindi natin na-discuss sa size and shape ng specimen natin. No? Nandito na tayo sa shape. Yung size pa lang ang na-discuss natin kanina. Sorry. Yung general pa lang yung na-discuss natin kanina on it. I think it's on the material characteristic pa lang yan. No? So wala pa tayo dun sa size and shape of the specimen. So for the size and shape of the specimen, and we're talking now of the laboratory sample that we are preparing. Normally, the specimen is a cylinder with height equals 12 inches and diameter of 6 inches. Okay? So if we look at the size, this is now the standard. 12 divided by 6 is 2. 2 times the diameter. So yun ang standard natin, no? So if we go on the size, this is 6 inches diameter. So this is size. So this is size or diameter. When the diameter is increasing, the strength is decreasing. Okay? So kung gusto mong mandaya sa test, lakihan mo yung diameter mo. Para nun, mas malakas siya. Okay? So, same shape but differing H over D. Okay, so now we look on the ratio of H over D. So the ratio here now is in terms of 12 over 2. Ito yung standard natin. So 2. Okay, so this is now H over D is 12 over 6. The cylinder is 2. Okay? Now, pag ang test specimen mo is cube, like in the British standard, it's actually a 6 by 6 by 6 cube. Your H over D is 1, somewhere on a 120 or 125% stronger yung mga cube natin. Okay? So, kung magte-test ka ngayon sa cube, where H over D is equal to 1, then you expect a higher or a stronger concrete specimen. Okay, the lower or the greater the ratio of H over T, the bigger, the lower the strength. Okay, so this is now a European 150 millimeter cube is 10 to 15% higher than the strength than the standard cylinder because H over D is equal to 1. So there's a slight error here in my graph. So this is only 115%. Okay? So banda lang siya dito, something here. Okay, so this is 100. Okay, moisture state. So standard procedure requires that the specimen be in the moist condition, surface dry at the time of testing. When you say on the moist condition, it must be surface dry, but inside it there's moisture inside the specimen. Air dried specimens show 20 to 25% higher strength than those in saturated condition. This is because of the pore pressure, okay, buildup, no? So there's water pressure on this. Kaya nagkakaroon ka ng higher strength. Pag air dry. So lower strength probably due to the disjoining pressure within the cement paste. So the rate of loading is 35 plus or minus 5 psi per second. So if the rate of loading is lower, it will lower the strength. If it is faster, it will increase the strength. So slow rate of loading, it will decrease strength. When the loading is fast, it will increase the strength. and this is the standard. When you say slow, less than 35. When it is fast, greater than 35. Okay, so let's discuss now the behavior on the various state of stress. But before that, I'd like to present to you the uniaxial tension energy description. No, so we know that concrete is weak in tension, but strong in compression. Okay, so why? So the reason for that is again the propagation of the cracks are rapid in tension than in compression kasi meron na siyang initial crack, no? Okay, so you need only a small energy to initiate the cracking of the matrix. So cracks rapidly propagate and interlink on the transition zone. So for uniaxial compression, it's less brittle than in tension because more energy are needed to form and to extend cracks in the matrix. For low to medium strength concrete, no cracks are initiated in the matrix up to about half of FC. So if this is your stress strain curve, stress strain, you will notice that if this is your concrete, at 1/2, at 0.5 F prime C, cracks are not yet initiated, meaning to say there are already micro cracks in the transition zone and some voids, capillary voids, but there are no force-inducing cracks yet within the matrix. So as this stress level, your concrete is said to be stable. Okay, stable shear band. Okay, in the transition zone exists, but still your concrete is still stable. At higher stresses, the cracks are initiated within the matrix, increasing in size and number. And the matrix in the transition zone cracks eventually join up. So there is no linking, no? It will link interconnectivity. So link or connect, no? So your micro cracks will connect with your transition cracks, your capillary voids will join, and suddenly a general failure surface will develop at around 20 to 30 degrees from the direction of the load. So that's how uniaxial compression behavior emanates in the test procedure. So concrete strength usually taken at 28 days age. So this is defined as the maximum compressive stress at a designated test age of a 6 by 12 cylinder cured under standard temperature and humidity condition and loaded longitudinally at a slow strain rate, so 35 psi per second. So note that other strength and physical properties such as elastic modulus impermeability are related to FC. Okay, so this finishes all the factors now of the strength of concrete. So let's move to our last topic, the behavior under various state of stress. So we focus more on the uniaxial compression. First, in the uniaxial compression. So your proportional limit is actually within 30% FC prime. So remember that, no? So at 30%, this is your 0.3 FC prime. You have what you call the proportional limit. So when you say proportional limit, this is the straight line, okay? So this is yet the linear, okay, stress versus strain. Okay, so this is strain and this is the stress. So the straight line gradually curves up when it reaches about 75% to 0.90 uh, of FC prime. So we're talking here of FC prime. So just put the prime there. So then bend sharply uh, at a critical stress and finally descends until fracture. Okay, so you will see now a sudden curvature here and then bends sharply somewhere here. Okay, so here at about 0.7 to zero point 0.9 of your FC prime, okay, and then something like this. So this is how your concrete curve, concrete stress strain curve looks like as defined here in our behavioral uh, graph. Okay, so from 30 to 50 FC prime percent, micro cracks in the transition zone extends, no cracking in the HCP matrix yet, so this is still stable. Okay, you call it stable condition. But from zero point 0.5 to 75, the crack system becomes increasingly unstable. And here we can now define what you call the critical stress. The stress at which the crack system becomes unstable also corresponds to the maximum volumetric strain at which the volume change in the reverse direction, expanding near or at FC prime. So above critical stress level, uh, concrete shows time dependent fracture. So under sustained stress condition, the crack bridging between transition zone and the matrix may lead to failure at a stress lower than FC. Okay, so sustained stress conditions mean that your loads are permanently uh, present in that situation. Okay, for the uniaxial tension, the shape is similar, but the sigma E relationship are similar, but in the other, of course, the other direction. And the interval of the stable crack propagation is very short, is shorter. So the stable crack propagation is abrupt and sudden. Okay, so you have a brittle failure in case of the uniaxial tension. So the failure in tension is due to a few bridging cracks rather than a numerous cracks in compression. So normally it's only about 7 to 11% of FC. Okay, so F compression and F tension relationship is only good for about 7 to 11%. So if you will look into the graph now of this is now your uh, graph. So this is now your proportional limit at okay at 30%, and here is the still the stable part 0.50. So here your concrete is still stable, but there are already cracks on the transition zone, of course. That's inherent. Around 75% up to around zero point 0.9 there this begins to become unstable. Okay, so at a certain point, which is somewhere at 0.75, there will be a reversal in the nature of the volumetric strain. Okay, wherein your concrete will now have a negative strain due to the fact that at that point your cylinder will have a shape like this. Okay, originally your cylinder is straight up like this. Okay, so the strain here, the lateral strain and the longitudinal strain here will no longer be positive because epsilon longitudinal, or let's call it epsilon 1, and these are epsilon 2 and 3, are this is already greater than epsilon 1. So epsilon 2 plus epsilon 3 is greater than epsilon 1. Okay, so if that is the case, your epsilon 1 minus epsilon 2 plus epsilon 3 is negative. Okay, so there will be now a change in volumetric strain from here, goes down to a negative ratio. Okay, so this is a normalized or a unit stress strain graph. Okay, so you call this now a critical stress. It's ranging from 75% to 90%. We don't want to reach this high in working stress procedure, but in strength design procedure, I will teach you how to deal with this when we reach that. Okay, so that ends my presentation, my lecture on concrete properties. I hope you understand the basic concepts in a simple language, no, that I uh, prepared and presented. Thank you.